Hi! In our last episode, we explored the properties of solids, liquids, and gases. We also focused on how water changes in phase and used the phase diagram to follow those changes. Today, we will zero in on how gases behave. Of the three phases of matter, the gas phase is the easiest to understand and picture in our minds. As we study it, we will see the scientific method in action. We will see how we summarize our observations into laws and explanations, such as the kinetic molecular theory. This theory explains how molecules move under different conditions of temperature and pressure. So don't move from your seats, and we will be back after a short break. Scientists don't stop at just observing. They also ask why things happen the way they do, or why things are the way they are. Once they find answers to these questions, then they can predict how things will happen. How do we explain the properties of different phases of water? How does matter change from one phase to another? If we could watch molecules directly, we would describe phase changes very accurately. But we cannot. So we have to use what we call a model. A model describes and explains things based on observations and sometimes using mathematical equations. A model is only an approximation or rough picture of the real thing. However, we accept a model as long as it explains all our observations well enough. Let's make some observations about matter. This beaker contains a mixture of mud particles and starch. Let's filter it. The filtrate is clear compared to the original solution. Now, using iodine, let's test this solution for starch. The dark color indicates that there is starch in the filtrate. What do these observations tell us? They tell us that matter exists as particles in varying sizes. These particles have spaces in between them. The mud particles are larger than the pores of this filter, which is ordinary writing paper. They're not able to pass through. The starch molecules, on the other hand, are smaller and so are able to pass through the filter. One model effectively describes and explains the three phases of matter, the kinetic molecular theory. It pictures matter as made up of particles. According to this model, the particles or molecules of a gas are greatly spread out and far apart. As a result, the attraction among these particles is so small and therefore insignificant. This is the case with water vapor. The particles are so small and far apart that we cannot see them individually. But once they come together or condense, we can observe them as water droplets on the outside wall of the cold bottle. From this observation, we conclude that there are water molecules in the air. According to the kinetic molecular theory, gas molecules are not only spread out, they also move randomly and constantly at high speeds and in straight lines. As the gas molecules move, They collide with each other and with the walls of the containers. For nitrogen gas, the molecules collide with each other 8.99 times 10 to the 28 times per cubic centimeter per second at 25 degrees Celsius and 1 atmosphere pressure. These collisions are assumed to be perfectly elastic. That is, the gas molecules do not lose energy upon collision. Unlike a ball, which on hitting a wall loses energy and slows down. The pressure of the gas is the force of the collisions of the molecules with a unit area of the wall of the container. The more frequent the collisions are, the higher the gas pressure is. Pressure will not change as long as the gas is in a sealed container and the temperature is kept constant. Here is a pressure gauge attached to a gas tank. It tells us how much gas is in the tank. High pressure means that more gas molecules are colliding with a unit area of the wall per second. If the pressure decreases while the volume and temperature remain constant, there are now fewer molecules colliding with a unit area of the wall. When the pressure drops below the normal value, it is time to refill the tank. Moving molecules have kinetic energy. The faster they move, the higher their kinetic energy. For molecules of different sizes but with the same amount of kinetic energy, the larger ones move more slowly. The smaller molecules move faster. This relationship can be expressed in the formula for kinetic energy. In a given system, or a specific body of matter being studied, such as this, there is an average kinetic energy for all of the molecules. Some molecules, however, move faster than the average value and have a higher than average kinetic energy. Others move more slowly. Their kinetic energy is lower than the average value. This average kinetic energy of the molecules is directly proportional to the absolute temperature. All gases have the same kinetic energy at the same temperature. At 0 degree Kelvin temperature, molecules would stop moving since they have zero kinetic energy. Let's recall the phase diagram of water. We saw that water enters the gas phase at high temperatures and low pressures. This is true for other substances as well. This means that gas molecules have a higher average kinetic energy than solid or liquid molecules. This also means that substances in their gas phase have fewer molecules per unit volume than in their solid or liquid phases. So, of the three phases, the gas phase has the lowest density. The higher kinetic energy of gas molecules keeps them moving at high speeds. This enables